Hello, this is Dr. Hanaa Assil, and today we're doing Unit 4 of IA2 Chemistry Edexcel. Reaction Kinetics is the first chapter. So this is the second part of the advanced level chemistry in the Edexcel. In reaction kinetics, we're talking about rates of reactions, and you should remember that the rate of a reaction is the rate of change in concentration of reactant or product per unit time. So for example, we could measure the concentration of reactants with time as the reaction proceeds. The concentration of the reactant will decrease. The faster it decreases, the faster the reaction. Or we could measure the concentration of product formed with time. As the reaction proceeds, concentration of product increases. The faster it increases, the faster the reaction. And you should note that the units of rate is concentration per time, so that is mole per decimeter cubed per second. If you remember from the AS syllabus, there is a Maxwell-Boltzmann distribution that shows the distribution of energy of molecules at a certain temperature. Remember that molecules that have effective collisions are the ones that have energy higher than the activation energy. So usually that is a small percentage of the total number of molecules. But if we increase the temperature, then molecules gain more kinetic energy, so there will be a larger percentage of the molecules with the required amount of energy for effective collisions, or energy higher than the activation energy. Also, if we put a catalyst, the effect of the catalyst is that it lowers the activation energy. So the energy needed for the particles to effectively collide is lower. So more molecules will collide effectively because more molecules have the energy more than the activation energy. Now, to study the rates of the reactions, there are different ways of measuring the rate. The easiest one, which we talked about in the previous syllabus, was measuring the volume of a gas per minute. So if the reaction is giving out a gas, we measure the volume of gas per minute using a gas syringe. Or we could put the flask on a balance and measure the loss in mass per minute. Another way of measuring the rate of a reaction is if we have iodine in the reaction. Either iodine is appearing or iodine is disappearing. In that case, the indicator we use is starch, and we titrate it usually with sodium thiosulfate. So if there is iodine in the solution, the starch solution turns dark blue-black. When the iodine is used up, or when there is no more iodine in the reaction, then the solution becomes colorless. So for example, this is a reaction that in which iodine reacts. So iodine here is disappearing as the reaction proceeds. So it produces HI. First, we need to neutralize this HI acid using sodium hydrogen carbonate. Then we titrate with sodium thiosulfate using a starch solution as an indicator. Of course, the end point is when there is no more iodine, so there is no more reaction between the iodine and starch, and the dark blue-black color changes to colorless. Another method of measuring the rate of reaction is colorimetry. Please note that this is colorimetry, not calorimetry. There is something else called calorimetry with an A. This is color, measuring the color. So this is colorimetry. This measures the appearance or disappearance of a color. So if one of the substances is colored, we can measure its change in concentration by measuring the transmittance of light at various times. Then a calibration curve is used to convert this transmittance to concentration, so we can follow the change in concentration of this colored substance. So of course we use colorimetry if one of the reactants or products is colored. So for example, reactions with bromine is a reddish brown solution. If it reacts, then the color disappears, and we can measure that using colorimetry. Or where we have iodine, also remember that iodine is a brown colored solution, and this in this reaction the brown color will slowly disappear, so we can follow the rate using colorimetry. Another method of following the rate is involves optical isomers. We're going to be talking a lot about optical isomers when we do the organic chemistry part, but for now, just know that an optical isomer is one in which the carbon atom is connected or bonded to 4 different groups. So in this case, the carbon is bonded to a hydrogen and to a CH3 and to a Br and to a COOH. So these are 4 different groups. This means that this can form an optical isomer, or we say that this is a chiral carbon. So this kind of substance would have an isomer that is a mirror image of it, but it is not superimposable on it. And what happens is, if we have a chiral carbon or an optical isomer, then this solution will, or the substance will change plane polarized light or deflect the plane polarized light, and we can measure the amount of deflection of the plane polarized light to determine the percentage or the concentration of this compound. So now that we know how to determine the rate, let's take a look at some of the questions that you may find about this topic. So this is a question that says, in aqueous solution, iodine reacts with propanone in the presence of a catalyst of dilute hydrochloric acid. Which of the following methods would be suitable for investigating the rate of this reaction? So let us see. He's saying measuring the increase in pH with a pH meter. This is something that forms HI, which is acidic. So the solution is becoming more and more acidic. So are we measuring increase in pH? No, the pH will be decreasing. So this statement is wrong. We need to measure the decrease in pH if we're going to use a pH meter. The other option is measuring the change in rotation of plane polarized light with a polarimeter. Well, do we have a chiral center here? We do not have a chiral center here, so it will have no effect on plane polarized light. Quenching with ice cold water followed by titration with acid. Well, quenching with ice cold water is fine. But then this is something that is forming an acid, so I need to titrate it with a base, not with an acid. Quenching with sodium hydrogen carbonate followed by titration with sodium thiosulfate, well, that is the correct answer, because we're forming an acid, so we quench it with a base, which is sodium hydrogen carbonate, and we titrate it with sodium thiosulfate to determine the amount of iodine or the change in concentration of the iodine in solution. Another question says bromine oxidizes methanoic acid to carbon dioxide. The equation for the reaction is this. Which of the following methods would not be suitable? Please remember that he's saying would not be. So which of these would not be suitable for measuring the progress of this reaction? Well, the first option here is colorimetry. Yes, I can use colorimetry because I have bromine, and bromine is colored reddish brown, and the disappearance of the color can be measured by colorimetry. So this can be suitable. I'm looking for which one is not suitable. Measuring electrical conductivity, yes, because we're forming more and more ions, so this will increase in electrical conductivity, and I can use that to measure the rate. Quenching and titrating with acid, well, quenching is okay, but titrating with a base, because I'm forming acid. So I can't titrate with an acid, I have to titrate with a base. So this is the one that is not suitable. Measuring the volume of a gas, yes, of course, because it is forming carbon dioxide gas. So I can measure the volume of gas per minute to measure the rate. In kinetics, the progress of a reaction can be followed by these 4 options. which method would be most suitable to investigate the rates of these reactions? Well, here this is a reaction of a halogenoalkane with hydroxide to give alcohol plus bromide. Well, can I use colorimetry? I don't have any colored compound in here. Measure optical activity. I don't have any chiral center. Measure of change in mass. Where no. Quenching with ice cold water followed by titration with acid. Yes, that would be correct, because then if I titrate with acid, then I can know how much of the OH minus is present. Now, the other reaction is iodine plus propanone to give the iodopropanone plus HI. Well, which one can I use for this? Of course, any reaction that has iodine, I can use colorimetry because iodine is a colored substance. Another possible question says, which reaction could have its progress continuously measured by measuring the change in pressure? Okay, change in pressure is actually another method of measuring the rate, but we need to have all of them gases, and we have to have a change in the amount of gases or the number of moles of gases in order to have a change in pressure. So we need gases. So first of all, C and D are wrong. So I need to choose between A and B. The problem with A is that the number of moles of gases before the arrow is the same as the number of moles of gases after the arrow. So you actually would not have a change in pressure. So the only one I can measure the change in pressure in is the reaction in B. Another thing that you need to know for this chapter is rate law. Now, the rate law is an equation that relates the rate of the reaction to the concentration of reactants. And to determine the rate law, we have to have experiments. It has to be determined experimentally. You cannot just look at the balanced chemical equation and from that determine the rate law. We need to do experiments. So, for example, let's take a look at this reaction. If he says, I want to write the rate law for this reaction. First of all, he has to give me experimental values. So let's say he did experiments, and first of all, he found that if he keeps everything constant but changes concentration of hydrogen, and he finds that if he changes the concentration of hydrogen, the rate changes in the same way. So doubling the concentration of hydrogen doubles the rate. Tripling the concentration of hydrogen triples the rate. From these experiments, then you can tell that the reaction is first order. We say if doubling the concentration doubles the rate, then the reaction is first order with respect to the concentration of hydrogen. Now, for the same reaction, he keeps everything constant and changes the concentration of the NO. And he found that if the concentration of NO is doubled, the rate increases 4 times. When the concentration of NO is tripled, the rate increases 9 times. That means it's actually to the power 2. In that case, we say that the reaction is second order with respect to NO. Now, first order with respect to hydrogen and second order with respect to NO, this is the rate law. We say rate equals a certain constant, which we call the rate constant, and we refer to it as K. We said it is second order with respect to NO, so we say it is concentration of NO squared, or to the power 2, times concentration of hydrogen to the power 1, because we said it's first order. So this is what we call the rate law. And if it is second order with respect to NO, first order with respect to hydrogen, then the overall order of the reaction is the sum of these. So overall, we say that this reaction is third order. Are we following? So K is called the rate constant. It's a constant for each reaction at a given temperature, because as we increase temperature, K increases. So please recognize these graphs. So this is the graph of K versus temperature. As temperature increases, K increases exponentially, not directly proportional. Okay, again, if he says, okay, we have decided that this is the rate equation for this reaction, then I can use it to get K. K would be the rate over concentration of NO to the power 2 times concentration of hydrogen. Now, he will give you values for NO, concentration of NO and concentration of hydrogen, so you can put that into the equation and get K. Now, the units of K differs according to the rate equation. So in this case, for example, we said it is rate. Rate is mole per decimeter cubed per second over concentration squared. That's moles squared to decimeter to the 6. Concentration of hydrogen, so that's mole per decimeter cubed. And in this case, if you cancel what's the same up and down, the overall units for K for this reaction is decimeter to the power 6, mole to the power minus 2, seconds to the power minus 1. Please note the units of K may differ from one reaction to the other. Okay, what about a zero order reaction? So we said first order, doubling doubles. Second order, doubling doubles to the power 2. If the concentration of the reactant is doubled and there is no change in the rate, then we say that the reaction is zero order with respect to that reactant. And in that case, the rate is just equal to K, because any concentration to the power 0 is 1. So rate is equal to K. And in this case, the units of K is the same as the units of rate, and that is mole per decimeter cubed per second. So remember that if something is zero order, rate is equal to K. And that means that change in the concentration has no effect on the rate. So we say the reaction is zero order. Now, first order, that means the rate is equal to K times the concentration. If we draw a graph of rate versus concentration, increase in concentration will increase the rate directly proportional. Second order, we said that means rate is K concentration to the power 2. And that means as I increase the concentration, the rate increases exponentially, not directly proportional. Please remember all of these graphs and what they are representing. So these graphs, for example, are rate versus concentration. Okay, we said, again, for a zero order reaction, change in the concentration has no effect on the rate. But the concentration of the reactant will decrease with time. So if we're doing concentration of reactant versus time, it decreases directly. So both graphs indicate that the change in concentration has no effect on the rate. And that means the graph has a constant gradient. For reaction that is first order, we said increasing the concentration increases the rate directly. And if we're doing a graph of concentration of reactant versus time, it will decrease with time. And that means increase in concentration increases the rate to the same order, so that is first. For reaction that is second order, we said as we increase the concentration, the rate increases exponentially. So the rate increases, for example, 4 times if the concentration is doubled. Let's take a look at some of these reactions. Did you pay attention to the graphs? Let's take a look at this. He says the rate of decomposition of compound X is first order. So the graph would be which of these? We said if it is first order, what does that mean? It means that if I increase the concentration, the rate increases directly. So that's my graph. Okay? Okay, what about this question? He says the decomposition of compound X is first order. Which is the correct graph? Now, this is a graph of concentration versus time. We said concentration, decomposition of compound X, that means the concentration is decreasing with time. When it is first order, we said this is the graph at B. That should be correct. Another question, which of the following graphs shows a reaction that is zero order with respect to Q? And that means if I change Q, what happens, the rate is constant. So it's not C. If you're looking at C says concentration of Q remains constant. No, we want to change concentration of Q, but we don't want it to affect the rate. So that is my first graph here. Okay. Another question, he says, in which graph is Y concentration of product and X time if we're talking about a zero order? So please look at what he's saying. What is Y and what is X? He's saying Y is concentration of product versus time, and it's zero order. So it's the graph that he has, Q, that he calls Q. Another question, in which graph is Y the rate and X concentration? So as the concentration increases, the rate increases for a first order reaction. So that's the same graph. Are we following? Please read the questions carefully. Sometimes they are a little confusing. Okay, so what do we mean by experimentally? He will give you a table in which he repeated experiments several times. So for example, this is the equation we were looking at, and he says he did an experiment in which this is the initial concentration of NO, initial concentration of O2, and the rate. And he's telling me to find out what is the order with respect to NO, what is the order with respect to O2. Now, to determine the order with respect to NO, I look at experiment 1 and 2. Can you see experiment 1 and 2? They both have the same concentration of oxygen. So you need to choose an experiment in which the others are constant. And the only thing we're changing is the NO that I'm looking at. So from 1 and 2, going from 1 and 2, the concentration has doubled. Concentration of oxygen is the same. So what has happened to the rate? The rate has quadrupled. And that means that the reaction is second order. We said if doubling doubles, that's first order. If doubling doesn't affect the rate, that's zero order. If doubling quadruples, then this is second order with respect to NO. Now, if I want to determine the order with respect to oxygen, then I choose two experiments that have different oxygens, but everything else is constant. So for example, if you look at experiments 1 and 3, the NO is constant. Now what is happening to the O2? The concentration is doubled. Now what happened to the rate? The rate also has doubled. Then the reaction is first order with respect to oxygen. Are we following? So concentration doubled, the rate doubled, that's first order. And that means if he says write the rate equation, we said rate equation, we say rate is equal to K into NO is second order, so that means concentration of NO to the power 2. O2 is first order, that means concentration of O2 to the power 1, and of course we don't write the 1. Then let's say he has the table and he tells me he wants to calculate K. He wants a value for K. Remember that K is different for different reactions. So if we say, for example, we use one of the experiments. So let's say experiment 1. I put in the value for the rate of that experiment, the concentration of NO for that experiment, and the concentration of O2, and then I can calculate K. Now, what is the unit? He will always ask for the unit. Okay, remember K has different units for different reactions. The rate of the reaction, which is 0.05, the rate is mole per decimeter cubed per second. And any concentration is mole per decimeter cubed. So he has down there the concentration to the power 2, so it is mole to the power 2, decimeter to the power 6. The other one is just mole per decimeter cubed, and then we cancel whatever is up and down in the equation. That is the same. So for this reaction, the unit is decimeter to the power 6, mole to the power minus 2, and seconds to the power minus 1. This is another reaction, and he says that he did experiments and he found that the reaction is first order with respect to Br minus, first order with respect to BrO3 minus, second order with respect to H plus, and he says write the rate equation. Again, you should know that the rate equation is rate is equal to K times concentration of Br minus, concentration of BrO3 minus, and concentration of H2 to the power, H plus to the power 2. And in this case, if he says calculate K and he gives you values, just put it into the equation. What about the units? Well, put in the units. The rate is mole per decimeter cube. The any concentration that we have is mole per decimeter cubed. If it is to the power 2, then it's mole to the power 2 decimeter to the power 6, and so on. And then cancel whatever is the same up and down in the equation, and you get the final units of K for that reaction. Are we okay with all of this? So let's take a look at this question. This is one of the questions that you will have, and he's saying he wants to determine the order of the reaction with respect to each of these. So let's take a look at iodide. If we're looking at the order of the reaction with respect to iodide, I choose two of the experiments or the runs in which the iodide is changing, but everything else is not. So experiment 1 and 2, or run 1 and 2, what is happening to the iodide from 2 to 1? It is doubling. And from 2 to 1, what happened to the rate? It also doubled. So doubling the concentration of iodide doubles the rate, so it is first order with respect to iodide. Now, if I want to take a look at the reaction with respect to H plus, that's the H2SO4. So I can look at experiment 3 and 4. Now going from 4 to 3, concentration of the H plus doubled, but the rate is almost the same. There is no effect on the rate. And that means it is zero order with respect to H plus. Are we following all of this? Okay. So this is a question. The rate equation for a reaction in which carbon disulfide decomposes is this. What are the units of K? You have to remember that to get the units of K from the reaction, from the rate law that we have, K is rate over concentration. Rate is mole per decimeter cube per second. Concentration is mole per decimeter cubed, and that's down there. So the final one, after canceling what is up and down, I get seconds to the minus 1. For this reaction, he gives me again the rate equation, and he says the concentrations of HgCl2 and C2O42- are increased by a factor of 3. Remember, if we increase by a certain factor, so what you have there is the concentration of HgCl2 is increased by a factor of 3. Now, the C2O42-, what would happen to the rate if I increase by a factor of 3? It is 3 to the power 2. And remember that the overall rate is the multiplication of these. So the overall, the rate will increase by a factor of 27. Are you paying attention? Okay. Again, let's take a look at this question. So here he gives me a table of concentrations of Y and Z, and he wants the order with respect to Y and the order with respect to Z. So let us take a look. In order to determine the order with respect to Y, I need to choose two experiments in which only Y is changing. So which experiments can I take a look at? I can take a look at experiment 2 and 3. So going from 3 to 2, the concentration of Y doubled. But what happened to the rate? There is no effect on the rate. And that means that the order with respect to Y is 0. So my answer is A or B. Now, what about the order with respect to Z? Now, I need to choose two experiments in which only Z is changing. So we look at experiment 1 and 2. So going from 1 and 2, concentration of Z doubled. What happened to the rate? It quadrupled. And that means it is second order with respect to Z. Okay? This one is another question. He's saying the rate equation of the reaction between hydrogen gas and nitrogen monoxide gas is this. If the concentration of both reactants is doubled, do you remember what we should do? He says, if it is doubled, that means NO is doubled to the power 2. H2 is doubled. and we multiply everything, so that is increased by a factor of 8. Another question, the chemical equation and the rate equation for the reaction between nitrogen monoxide and bromine is this. When the concentration of NO is halved and the concentration of bromine is doubled, half to the power 2, doubled, overall, the reaction will be half. Can you see what we did? Another question, he gives me numbers and he says, what is the value of the rate constant? Okay, we said, how do we calculate the rate constant? K would be from the rate law, it is the rate over A to the power 2. Of course, B to the power 0 is just 1. It doesn't affect the calculation. So this comes out to be 0.001, which is 1 times 10 to the minus 3. Half-life. What is half-life? Half-life is the time taken for the concentration of a reactant to fall to half of its original value. So if we draw concentration, a graph of concentration versus time, and we want to determine what is the half-life. The half-life is the time taken for the concentration to fall to half. So if he's starting with 0.2, he changes to 0.1, and this is one half-life. Changing from 0.1 to half of that, which is 0.05, that's another half-life. Changing from 0.05 to 0.025, that's another half-life. Now, for this reaction, we find that the half-life is constant. And if we can determine that the half-life is constant, every time the concentration falls to half of it, it takes the same time, then this reaction is first order. So remember, if half-life is constant, reaction is first order. If we have a question like this, the half-life of a reaction is half the time for the reaction to go to completion, or the time taken for the reaction for the rate to half, or the time taken for concentration of a reactant to half, or the time taken for any concentration of a reactant to half. It is actually the time taken for any concentration of a reactant to become half its original value. Okay? Hydrogen peroxide decomposes in a first order reaction. The half-life of this reaction is 60. That means every time it falls to half the concentration, it takes 60 seconds. Now, in an experiment, the initial concentration of hydrogen peroxide is 0.1. So we're starting with concentration 0.1. What is the concentration after 120 seconds? Well, you should realize that in 120 seconds, you have two half-lives. So after the first half-life, after the first 60 seconds, the 0.1 will fall to 0.05. Now after the second half-life, that means the second 60 seconds, it will fall to 0.025. That means after 120 seconds, the concentration is 0.025. Are we following this? Okay. Another question. The gaseous first order reaction is this, was found to have a half-life of 20 seconds when the initial pressure is 2 atmospheres. Now, when the initial pressure is increased, what happens to the half-life? I will tell you that the half-life does not depend on the pressure. It will always be the same for the same reaction. Okay? So, if I have first order reaction, I can calculate K from the half-life. So if he tells me he has a certain half-life, then I can get K. It is always 0.693 divided by the half-life if we're talking about a first order reaction. What about a zero order reaction? If I am drawing a graph of concentration versus time, and I find that the half-life decreases. So every time the amount falls to half what it was, the half-life, the time taken, decreases. Then this reaction is zero order. So remember, if the half-life is constant, it's first order. If the half-life decreases, it is zero order. If the half-life increases, it is second order. So this is the graph you get if we're talking about a second order reaction. The half-life keeps increasing. Okay? Then we have something called the Arrhenius equation. You're not required to memorize this equation. He will usually give it to you. The equation says ln of K, which is the rate constant, is equal to minus energy of activation over RT plus a certain constant. And that means if I draw a graph of ln K versus 1 over T, always ln K is usually a negative value. So the graph looks like this. It's a negative gradient. So if you get the gradient of this, the gradient is equal from the reaction, from the equation up there, the gradient is minus EA over R because you're plotting ln K versus 1 over T. So the gradient is minus EA over R, and I can use that to get EA. Now, what are the units of EA? The units of EA are either joule per mole or kilojoule per mole. So, to determine activation energy, the variation of reaction rate with temperature is investigated. He gives you this equation, and he says the activation energy could be obtained by plotting a graph of what? We said if we have this equation, which we call the Arrhenius equation, and I plot a graph of what? Of ln K versus 1 over T. So we plot a graph of ln K versus 1 over T. The gradient is minus EA over R. To determine the activation energy, a graph was plotted of ln K against 1 over T, and the Arrhenius equation is this, and we said the gradient of this graph is minus EA over R. Remember, when you draw a graph of ln K versus 1 over T, the gradient is minus EA over R. Okay, reaction mechanisms. What is a reaction mechanism? It is the step-by-step sequence of reactions by which the overall chemical change occurs. So usually when we write a reaction, it doesn't happen just in one step. Usually it happens in more than one step, and the mechanism can be determined experimentally. So if I have this reaction, for example, and he gives me a mechanism now, this mechanism, for example, that he gives me says that there is a fast step in which the NO first changes to N2O2. Then there is a slow step in which the N2O2 reacts with the hydrogen to form something which then reacts after that. Now, what is the rate determining step? First of all, remember that the rate determining step is the slow step. So he's telling me that step 2 is slow, then that is what we call the rate determining step. Then, in order to determine the rate of the reaction or the order with respect to these reactants, we have to take in the reactants that are in the slow step or anything before that. So here, which reactants are involved in the rate equation? Looking at this mechanism, I will tell you that it is anything before step 2, including step 2. So which reactants do we have in step 1 and 2? We have NO, and we have a coefficient of 2, and that means it's second order with respect to NO. And then in step 2, I have the H2, and I have only one coefficient, so it is first order with respect to hydrogen. And then that means that overall the reaction is third order. Again, if we have a reaction, let's say I2 plus H2 to give to HI, we said this will happen in a series of steps. So let's say it happens in these two steps. First, the iodine changes to iodide, and then the iodide reacts to form HI. First of all, if I have something that is formed during the mechanism and then used up so that it doesn't show in the final equation, for example, the I minus here is formed in the first step, used up in the second step, so overall we don't have it in the equation. So we call it an intermediate. So the intermediate here is the I minus. And then if he says what is the rate equation, the rate equation we said has to include anything that is in the slow step or anything before that. So he's telling me that the reaction, this reaction M plus 2N, whatever gives P plus Q, and this is the mechanism. M reacts with N first in a slow step. That means that the rate equation must include both M and N, and that means it is first order with respect to M and first order with respect to N. Okay. Another question would be with respect to reactions of halogenoalkanes with alkaline solution. So for example, we said if I have a tertiary halogenoalkane, when we do this in organic, we said the bromide leaves first to form a carbocation, and then the hydroxide ion attacks the carbocation to form the alcohol. Now, this kind of reaction is called SN1, nucleophilic substitution involving one reactant. So my first step involves only one reactant in which the halogenoalkane loses the halogen. But then if we're talking about this, then we say that the reaction is first order with respect to the bromoalkane, because that first step is the slow step, and it doesn't involve hydroxide ions at all. We haven't reacted hydroxide ions yet in that first step, so we say it is zero order with respect to the hydroxide ion. So this is what happens if we're using a tertiary halogenoalkane. In that case, the rate is K times the concentration of the halogenoalkane. The hydroxide does not affect the rate. But if we're talking about a primary halogenoalkane, now a primary halogenoalkane reacts in another mechanism which we call SN2. This is nucleophilic substitution involving two reactants at the same time. So it forms an intermediate in which the bromide is slightly moving away and the hydroxide is slightly coming in. And then the bromide leaves and the hydroxide attaches itself. So this is SN2, and this, remember, happens with a primary halogenoalkane. In this case, the first step, which is the slow step, involves both the hydroxide and the halogenoalkane, and that means that the rate is first order with respect to both the halogenoalkane and the hydroxide. And these different mechanisms, if we say why does this happen, it's because the tertiary halogenoalkane, when it forms a carbocation, you should realize that this carbocation is more stable as a tertiary because the alkyl groups which are the CH3 groups around it, they have an inductive effect. That means they sort of donate electrons to stabilize this tertiary carbocation. So this is more stable than if we were talking about a primary carbocation. Another reason is that the primary has more space for the hydroxide to attack directly. If we were to have the hydroxide attacking directly on a tertiary, this is the alkyl groups will not allow this direct attack. So that is why we have different mechanisms if we're talking about tertiary or primary halogenoalkane. So let's take a look at this question. A bromoalkane was hydrolyzed by an aqueous alkaline solution. The reaction was found to be first order with respect to bromoalkane and zero order with respect to the hydroxide. So what is he talking about? First order with respect to bromoalkane, that means the bromoalkane formed a carbocation. That means we're starting with a tertiary. So this is a tertiary halogenoalkane in which we have SN1. Now, which of these is tertiary? It is D. Remember that tertiary means the carbon is attached to three other carbons. Nitrogen monoxide and hydrogen react to form nitrogen and water. The steps and the mechanisms are this. So he's telling me that the first one is fast, second one is slow. Which statement about the reaction is correct? Is step 3 rate determinant step? No. First of all, we said the rate determinant step is the slow one. So A and B are wrong. So step 2 is the rate determinant step. What is the overall order? The overall order is what? We have NO and hydrogen. The overall order is 3 because it's going to be second order with respect to NO and first order with respect to hydrogen. Again, he's saying decomposition of hydrogen peroxide is this, the rate equation is this, which one is consistent with the reaction mechanism. Okay, there is only one step in the reaction mechanism. Well, there is no way that you're going to know that. The catalyst is used up, there is no catalyst that is used up. Now, the slowest step is the reaction of two molecules of hydrogen peroxide with an iodide ion? Well, no, because it's first order. So the slowest step is the reaction of one molecule of hydrogen peroxide with iodide ion. If we were talking about two molecules, it would be second order. The rate of the reaction between hydrogen and bromine is this. What can be deduced about the rate from this for this reaction from its equation? So looking at the equation, what can you tell about the rate? Actually, you can't tell anything from the chemical equation. Remember, we cannot tell the rate of any reaction simply by looking at its chemical equation. A halogenoalkane reacts with hydroxide to form an alcohol. The rate equation for the reaction is this. Which of these statements is incorrect? Okay, the first one says rate is proportional to the concentration of Rx. Yes, rate is proportional to the concentration of Rx. Now, Rx is a primary halogenoalkane. Remember, he's saying it's first order with respect to the Rx, and the hydroxide has no effect on the rate. It's not included in the rate equation. That means that the Rx has to be tertiary, not primary. So this is the one that is incorrect. The reaction is SN1, yes. A carbocation intermediate forms, yes. Okay, we have two types of catalysts. We have homogeneous catalyst and heterogeneous catalyst. A homogeneous catalyst is the one in which the catalyst is the same physical state as the reactant. So if my reactants are solutions, then my catalyst is also a solution. If my reactants are solids, then my catalyst is also a solid. So the catalyst in this case forms an intermediate compound with the reactants, which then breaks to form products. For example, the reaction of persulfate with iodide ions, we use iron 2 plus catalyst. So the iron 2 plus reacts first to form an intermediate, and then this breaks up to react with the other reactant. So this is all solutions, and this is called a homogeneous catalyst. A heterogeneous catalyst is where the catalyst is different physical states. So we're doing solutions reacting together, but my catalyst is a solid, for example. In this case, the reactants are adsorbed on the surface of the catalyst. This weakens the bonds of the reactants and the reaction occurs. And then when the products form, they are released from the surface of the catalyst. So for example, we said if we have a reaction of H2O2, the decomposition of H2O2 requires a catalyst like manganese dioxide, which is a solid. Or we said the Haber process where we have nitrogen gas plus hydrogen gas to give ammonia gas. And in this case, my catalyst was iron as a solid. So this is heterogeneous catalysis. Okay, thank you for listening to this video. I hope it was helpful. Please keep listening. The next videos will be questions and answers on these topics. Thank you.